Now that we have an idea what a limit is and what it looks like on a graph and what it looks like on a calculator or on an Excel spreadsheet, we're going to learn how to mathematically determine the value of limits. The first rule that we need to know is what's called the substitution rule. Okay? In many cases, it's going to be true that the limit as x goes to a of our function f is going to be the same thing as the function value at a. What does that look like in terms of a picture? This is a, and f of a is up here. And if we say that the limit as x approaches a for f of x is the same as that number, that means on both sides of that number, the graph goes to that same y value. Okay, for a lot of the functions that we've studied, that's the case. And so this is the first thing we'll always do when we try to evaluate a limit. Okay, we will always substitute in the value of x that we're approaching into the function. If we get out a number, we'll be finished. Unfortunately, that's not going to happen most of the time for the limits that are of any interest to us. Okay, but let's just take a look at some examples. The limit as x approaches 2 of 2x minus 1. The substitution rule says substitute in the 2 for the x and see if you get out a numerical answer. In this case, you'll get 2 times 2, 4, minus 1, which is 3. That's a numerical answer, so you're finished. Second example. Limit as x approaches 1, x minus 1 over x squared. We do a substitution. 1 minus 1 is 0 in the numerator, and 1 squared is 1 in the denominator. And so we get a numerical answer of 0. That's the value of the limit. Limit as x approaches pi over 4 of cosine x. We do a substitution, pi over 4 for x, and we'll get the cosine of pi over 4, which is the square root of 2 over 2. Numerical answer, so we're finished. Most of the limits that we deal with won't be like that, and we're going to run into certain situations. The first situation is going to look like this. When we do a substitution, we're going to get a number not equal to 0 divided by 0. Let's take a look at two quick examples here. The limit as x approaches 1, 4 over x minus 1. That's 4 over 0 if I do a plug-in. Now, in pre-cal that's undefined. Okay, but that doesn't tell us much in calculus. So as far as the limit's concerned, this limit does not exist. Over here, if we do a plug-in, we also get 4 over 0. So this limit does not exist as well. Now, what would happen on the graph of these two functions? Well, let me go to a quick grid here. If we took the time to graph these functions, we would see something like this. The first graph would have a vertical asymptote at x equals 1, but would go in different directions close to x equals 1, while the second graph would also have a vertical asymptote at x equals 1, but would head in the same direction around x equals 1. So, moral of the story is number that's not equal to 0 divided by 0 as a limit is always going to be does not exist. Okay, the graph will have a vertical asymptote, and you'll have to do some further investigation to determine whether the graph does a split at that point or whether the graph stays together at that point. Okay, so for example, this limit, if you knew what the graph looked like, could also be called positive infinity because from both sides of 1, the graph heads towards positive infinity, gets very large. Over here, though, you can't say that because on the right, the graph heads towards positive infinity, while on the left, the graph heads towards negative infinity. Overall, though, number divided by 0 does not exist. The issue that we spend most of our time dealing with is this issue right here. 0 divided by 0. Real quick, let's do some plugins to show you that these two are 0 over 0. You get 1 minus 1 in the numerator and 1 minus 1 in the denominator. Over here, you'll get 4 minus 4 in the numerator and 16 minus 32, which is negative 16, plus another 16, 0. All right, what on earth does 0 over 0 mean? Okay? Remember, issue number 1 said number not equal to 0 in the numerator and 0 in the denominator does not exist. What does 0 over 0 mean? In calculus, this has the name indeterminate. That means that at this point, it cannot be determined what the limit is, or even if the limit exists. Cannot be determined. That's what indeterminate means. So we have to now do some more work to remove one of these zeros so that it's no longer indeterminate. What will that work be? Well, some algebra can be done. When we get to some trig limits, there'll be some identities that we can use. Okay, but things that should come somewhat naturally to us, and some techniques that we'll actually learn along the way here. If I'm an algebra student, then the first thing that makes sense to me is to factor that numerator as a difference of two squares. So I'm going to write this as the limit as x goes to 1 of x minus 1 times x plus 1 divided by x minus 1. In section 2.3 of your textbook, there are a lot of limit laws, things that you're allowed to do with limits. And one of those limit laws says that, let me write it up here, the limit of, and I'll use some abbreviations here, the limit of f times g is equal to the limit of f times the limit of g. In other words, the limit of a product is the same thing as the product of the two limits. And that's a property I'm going to use right here. I'm going to split this into two different limits. So the limit as x approaches 1, I'm going to split this up. I'm going to write the denominator as x minus 1 times 1 and show you that this is a legal move here. X minus 1 over x minus 1, that's the first part, and then times the limit as x goes to 1 of what remains, which is x plus 1 over 1. If I multiply those two fractions together, I'd end up with what I have in this line right here. And the reason I did that is because I'm removing an unnecessary 1 from this fraction. X minus 1 divided by x minus 1 is always equal to 1 except when x is 1. But x is not 1 when we do a limit. X approaches 1. So this first limit is 1. Now I'm left with this second limit, and what I'm hoping is I can do a plug-in and get a numerical answer. And it turns out that I can, and I'll get an answer of 2. So this limit that started off as being indeterminate ends up being a numerical value of 2, and that was done by removing the 0 over 0 problem by factoring in this case. Now, let's look at the second example over here. I'm going to probably have to do a similar idea, and it makes sense to me as a former algebra student to factor the denominator if possible. So the denominator can be factored as x minus 4 times x minus 4. Okay, I see that x minus 4 is a factor of both the numerator and the denominator. So if I factor the numerator as x minus 4 times 1, I can now separate this into two different limits. If you're wondering, yes, it is necessary to write limit on each line. It's good mathematical notation. It also reminds you that I have not actually taken the limit yet, so the plug-in has not occurred. All right, x minus 4 over x minus 4, what remains is 1 over x minus 4. The first limit is x minus 4 over x minus 4. That's always equal to 1, except when x is 4, and x is not equal to 4. X is approaching 4. And so the limit as x approaches 4 of 1 is 1. What's left over here? The limit as x approaches 4 of 1 over x minus 4. I do a plug-in, and I'll get 1 divided by 0. From the previous slide, that's going to be a limit that does not exist. That's some kind of vertical asymptote. So in this case, indeterminate ended up being does not exist. In the first case, indeterminate ended up being a number 2. What happens is whenever you have indeterminate, the limit could be any real number until we unravel the facts and find out what it really is. Now, when we have piecewise functions and we're asked to find a limit, if the limit being asked for is at the breakpoint, so this function here splits its personality when x is 4. That's where the limit's being required. And you'll notice that this function is not even defined at 4. So remember that if a full limit exists, that means that the two one-sided limits have to be the same. So when you have a piecewise function and the limit that's being asked for is at the breakpoint, you need to split it into two different limits. The limit as x approaches 4 from the left, and the limit as x approaches 4 from the right. Now, which part do we use? Well, if x is less than 4, it says up here we use this first piece right here. So 2x squared minus 3x plus 12. And when x is more than 4, I'm supposed to use this piece here, 5x plus 12. Okay, now I'm ready to do some plugins. So here I'm going to get 2 times 4 squared minus 12 plus 12. The 12's cancel, and I get 16 times 2, or 32. Over here I do a plug-in, and I get 4 times 5 plus 12, also 32. These two limits are equal, and that means that the full limit exists and is equal to 32. So the limit as x approaches 4 of f of x is 32. Notice that if I had asked you for something else, like the limit as x approaches 2 of f of x, you would not have to split that into 2, because when x is approaching 2, you can use this function for f. Or if I'd asked you for the limit as x approaches 10 of f of x, you would not have to split that up into two limits, because x approaching 10 would fit 5x plus 12 on both sides of 10. So piecewise functions only need to be split when the limit being asked for is at the breakpoint. Okay, the last example we're going to look at is one that involves absolute value functions. Whenever you have an absolute value function, the first thing we need to do is to convert the absolute value. So the absolute value of x minus 1 becomes a piecewise function, becomes x minus 1 if x is bigger than 1, and it becomes the opposite of x minus 1 when x is less than 1. What does that mean? It means the absolute value of x minus 1 divided by x minus 1, which is what we have started with here, is equal to x minus 1 over x minus 1 if x is bigger than 1, and the opposite of x minus 1 over x minus 1 when x is less than 1. Which means we can simplify that a little bit, because x minus 1 divided by x minus 1 is always equal to 1, as long as x is not 1. And x minus 1 over x minus 1 with a negative in front is equal to negative 1, as long as x is not equal to 1. Okay, so now what do we need to do? I have a piecewise function. I need to evaluate the limit where the function breaks, so I need to look at the two one-sided limits and see if they are the same. So the limit as x approaches 1 from the left of my function, when I simplified it, it is always equal to negative 1 when x is less than 1. And the other side, the limit as x approaches 1 from the right, is always equal to positive 1. Since these limits do not match, they're not the same, then the full limit as x approaches 1 of this function does not exist. Okay, if I was to sketch a quick graph of that, this is what you would see. This being 1 right here. To the left of 1, you would see just a horizontal line that continues until x became 1, where you'd see an open circle. And then to the right of 1, you'd see a horizontal line that stops when x equals 1, extended in the other direction. Okay, we call this a jump discontinuity because the function jumps y values. But you can clearly see at x equals 1, there is not a single y value that the function approaches. There are actually two, and that's the reason that the limit does not exist.